So for this video, we are going to define major head loss or how it's derived. We're going to derive major head loss, and then we are going to talk about how to solve for major head loss in a pipe flow problem. So for fully developed laminar flow in an inclined pipe, recall that major head loss is the viscous effects from the conduit wall. So we're not talking about there's no bend, there's no valve, there's nothing. It's just a section of pipe that is fully developed laminar flow. So I've chosen a section that's already fully developed in laminar. So let's take our mechanical form of the conservation of energy equation in the head form. And if the velocity is fully developed, meaning the velocity doesn't change from point A to point B in a pipe, then those velocities are the same, and that'll cancel out on the left and the right hand side of the equation. And then if I say this is an incompressible fluid, that means the density doesn't change from the inlet to exit, so the subscripts go away, so density is just density. And then if there's no turbines or anything, there's no pumps, it's just a section of pipe, then the pump or turbine head goes away, and that becomes zero as well. And I can rearrange this equation. I'm going to put a little dotted line around that because I want to save that for later, and say that my major head loss, is equal to change in pressure times the change in elevation divided by the density times the acceleration of gravity. And it doesn't matter that it says inlet, exit density are the same, so it should just be density there in the denominator. Now recall back to a couple lessons ago where we talked about how to determine or derive or calculate, in this case, the mean velocity of fully developed laminar flow. So let's take a look at that equation. Now I'm going to replace this sign of alpha with the definition sign of opposite over hypotenuse. So the change in elevation is that opposite of an inclined pipe divided by the length, which is the hypotenuse, and I can substitute that in, rearrange it, and I get 32 times the dynamic viscosity times the length of the pipe times the mean velocity divided by the density times acceleration of gravity times the diameter squared is equal to the change in pressure times the change in elevation divided by the density times acceleration due to gravity. Because incompressible, density inlet, density exit doesn't matter. Density is density. So the right-hand sides of both of those equations in the dotted yellow lines are the same. That means the left-hand side of the equation is the same. So I can make the left-hand sides of the equation equal to one another. And I can say that my major head loss is equal to 32 times the dynamic viscosity times the length times the mean velocity divided by density times the acceleration due to gravity times the diameter squared. Now, I'm going to do a little math trick here. And I'm going to multiply the top and the bottom by 2 times the mean velocity. Now, you'll agree that if I multiply the top and the bottom, the numerator and the denominator by the same thing, it cancels out, so it doesn't change the value whatsoever. But I'm going to do this so that I can incorporate a term here that we use heavily in fluid dynamics, which is Reynolds number. So you can see, if we kind of search through there like a puzzle, we can see that if with the terms that I highlighted, that's the inverse of the Reynolds number. So I can rewrite major head loss in terms of Reynolds number, and I get the equation you see here. My major head loss is 64 over the Reynolds number for internal flow, hence that subscript D, times the ratio of the length to the diameter times, and look at that, we get the velocity mean squared over 2g. It just looks just like velocity head, right? So this is the equation 9.22 for major head loss, but this is for laminar flow only. So let's hold on to that equation and let's move on. So if I have major head loss, and I'm starting with the major head loss equation for laminar flow, equation 9.22, let's get this in general form. So where we have that 64 divided by the internal flow Reynolds number, I'm going to call that F, or the friction factor. So in general terms, I can write equation 9.23 that my major head loss is the friction factor times the ratio of the length of the pipe to the diameter of the pipe times the velocity head from the mean velocity. And this is called the Darcy-Weisbach equation, and this is how we will compute major head loss in our pipe flow problems. So you can see from this equation, head loss depends on the following thing. It's a function of the length of the pipe, the diameter of the pipe, the mean velocity of the flow, and the friction factor. She said, okay, I got the friction factor is 64 over the Reynolds number for laminar flow, but what is it for turbulent flow? What is it for transitional flow? Well, let's again look at that Darcy-Weisbach equation. And now we're talking about friction factor for turbulent flow. So for turbulent flow, the friction factor is based on experimental results. So here's one empirical result equation that's generally accepted in the community as a way to determine the friction factor for turbulent flow. And it's the equation you see here before you. And you know everything in that equation. You see that you got the Reynolds number for internal flow raised to the 0.09. You got the log base 10 of everything inside the parentheses. Notice that everything inside the bracket is raised to the negative 2 power. And that's all times 0.025. But you have that epsilon in there in equation 9.25. And this is an equation you can use to find your friction factor. It will work. And this is one you want to write down. But let's look at epsilon. What is that epsilon? First of all, this is called the Swamy-Jain equation. And epsilon is what we call the pipe roughness. So how do we use the pipe roughness? How do we obtain the pipe roughness? Right now, it's a variable within your equation that you don't know. So let's look at a Moody diagram. This is a Moody diagram, or a graphical depiction of the Swamy-Jain equation. I want you to note the left and right-hand sides, and so the y-axes on either side, they are different, and then the x-axes across the bottom are all in logarithmic scales. So that's something important to look at when you're reading this. Now, left-hand side, you'll see the friction factor. I'll show you how to use this. You can see in the laminar region, less than 2,000 on my Reynolds number. You can see my x-axis is the Reynolds number. Less than 2,000, I'm going to use the equation. My friction factor is 64 divided by the internal flow Reynolds number. You can see from 2,000 to 10,000, or 10 to the fourth, I have transitional flow. So I'm oscillating back and forth between laminar and turbulent. And then beyond that, I'm in turbulent flow region as the Reynolds numbers increase. So on the bottom left-hand side here, you see different types of materials. And this is not an all-inclusive list. This is just general. These are the ones we use in this class. And you have these columns for epsilon, or the friction factor. And this is figure 9.5 in your textbook. And this is not in your reference book, so this is something you'd want to tab. You may need this on an exam or on homework. So you can see on the bottom, Reynolds number. The equation for Reynolds number for internal flow is right there on the bottom for you, with the characteristic length being diameter. And let me blow up that little table on the bottom for our friction factor. Notice the units on friction factor, on roughness. On my roughness, I have a column in feet, and I have a column in millimeters. So depending on the material and depending on the unit system you're working in is where you're going to obtain this value. And you got to make sure your units are consistent. Note that that's millimeters, not meters. That's feet, not inches, when you're determining your relative roughness, which is on this right-hand side, this y-axis on the right-hand side, which is the pipe roughness divided by the diameter. And that's relative roughness. So the equation is right there. I'm going to take whatever material I have. I'm going to take its roughness. I'm going to divide it by the diameter, and I'm going to get the relative roughness. And that's how I'll use this diagram. And I'm going to show you an example of that here in a second. So let's clean up our Moody diagram. And let's just say we have some problem where I'm given some material, so I'm able to look up my roughness. And I know the diameter of the pipe, so I can compute the relative roughness and making sure my units are the same. So let's say I do that and I say my relative roughness is 0.00008. So I'm going to find 0.0008 on the right-hand side here. I'm going to index the relative roughness, and it's between 0.0005 and 0.0001. So I'm going to, based on my knowledge of logarithmic scales, to the best of my abilities, determine where that value is, and I'm going to create a curve that mimics the curves for each relative roughness. Now, I can also compute my Reynolds number. So let's say I compute my Reynolds number, and I get my Reynolds number is approximately 1.4 times 10 to the fourth. Well, 1, that tells me I'm in the turbulent region because I'm greater than 10,000. So I'm going to index here on the x-axis that Reynolds number. An important thing I want you to note, besides the fact that it's logarithmic, so it's not as clear just going, oh, here it is, it's right in the middle, you got to look at how everything's spaced out. So if you get confused in how things are spaced out, let's start here. 10 to the 3, so that's 1,000, right? This is 2,000, 3,000, 4,000. You can see the gap between 1,000 and 2,000, how it continually grows smaller between 3, 4, 5, 6, 7, 8, 9, and then 10,000. So common student error is to say, let's say they had 1.4 10 to the fourth is to go, oh, it must be somewhere here because these are all 10 to the fourth. These are all 10 to the third. So you have the 10 to the fourth value. Everything to the right of that is 2 times 10 to the fourth, 3 times 10 to the fourth, etc. 10 to the fifth. Everything to the right of that is 2 times 10 to the fifth. That is a common error. 3 times 10 to the fifth, so on and so forth. Right? So I'm going to draw a vertical line where I estimate a Reynolds number of 1.4 times 10 to the fourth to be. And I'm going to look at where those two curves intersect, and then I just read straight to the left to get my friction factor. So in this case, my friction factor is 0.029. So I can do this, or I can use the Swami-Jain equation, either or. Some people prefer to use the graph. It's a little bit faster, but obviously a little less accurate. You have to kind of assume values. You have to eyeball it, whereas the Swami-Jain will give you a more accurate depiction. In fact, this graph is made using the Swami-Jain equation, so you should get the same answer. A couple observations to take a look at. Notice that my friction factor being on the left, as my Reynolds number increase, so as the velocity, let's say, of my flow increases, or the dynamic viscosity decreases, you can see that I start off relatively high on my friction factor, but for every single relative roughness, I eventually decrease to a point where it becomes basically linear, and I have the same, regardless of my Reynolds number, then the same friction factor across. So just a couple observations. You can use either or, the Darcy-Weisbach or the Moody diagram. Those are, I hope I point out all the obvious shortfalls or mistakes that cadets make. If you have any trouble with this, please see your instructor.